Okay, let's have a class, and we will move to exam 3. Exam 3, we will talk about biochemistry and genetics. The arrangement will be today, we will do an overview, and then we'll talk about the basically is aerobic respiration cycle, and we will talk about is calculate the ATPs from glycolysis, citric acid cycle, and also fermentation. And then we are going to move on to the DNA replication, transcription, and translation. And the last one, we will talk about lacto-operon. So this is basically the main topic we're going to cover in this section. Okay, so if you are at the same time, you are taking the genetics class or biochemistry class, certainly will help, but it will be a little bit different because we are talking about is bacteria, is prokaryotes. What you learned in your biochemistry class basically is eukaryotes. So there is a little bit difference. Okay, so keep in mind about that. Okay, the first thing, since we talk about metabolism, so always remember metabolism have two parts, which is catabolism and anabolism. Catabolism is always you're using energy. Okay, they break down large chemicals to the simple, smaller one, exogonic. Anabolism is endogonic. You're using energy. Small molecules to biosynthesis has become large molecules. In here, in this class, we're going to only talk about the catabolism. Anabolism we will not mention too much. Because for the bacteria, we pay much attention to catabolism. We don't really care about too much here for anabolism. This is another class which is microbiology physiology. For microbiology major students, they may talk much more detail about that. Here we're only going to talk about the catabolism. Okay? This is the slides which tells you using another picture format to explain catabolism and anabolism. So you can see catabolism, energy source, glucose. They use the energy, they generate waste products, could be acids, carbon dioxide. That's a typical waste to generate. And the bacteria also going to use the energy with other energy resource like nitrogen, sulfur, and then have their subunits, let's say amino acids, nucleotides, lipids, then use energy become a macromolecular, and finally become their cell structure, like cell wall, membrane, ribosome, nucleic acids, surface structures, all those things. Okay, so that's a very good picture to explain what is catabolism and anabolism, but always remember metabolism has those two parts. Okay, next couple of slides. I'm going to combine them together. We will talk a little bit about the physics. So that is somehow a little bit different, a little bit difficult, but we try to find a way, is you can understand it. First thing first is thermodynamic. Thermodynamic rules. Okay, there are two basic rules. The first law, I'll put a quotation mark there. This is not really a law. First law and second law. Okay, what is the first law? This means energy never create or destroy, only transfer from different formats. So I gave you a very simple example. I don't know how much you know about physics. When I was in high school, we always do these type of puzzle questions. So let's say there's a ball right here. Okay, the ball will go down. And there is a car right here. Okay, what is this energy here? This is the potential energy. Is that right? And when the ball comes down, they go here, and this car will start to move, this will become kinetic energy. So this is kind of like use potential energy become a kinetic energy, and we could do a calculation. This energy here is mgh, and this kinetic energy area is 2.5 mv. So based on the energy balance rule, the mgh equals 2.5 mv. So the velocity, it depends on gh, which means it's not related to, we assuming they are the same weight, okay? It's not related to the weight, it's related to how high it is, because that gives you potential energy. Now, obviously, later on becomes difficult. You could be M1, M2, then you do all these calculations, it becomes difficult. Okay, so that's a different story. It could be M1 divided by M2, all kinds of puzzle concepts. So just give you examples. That's the first one. So energy never created or destroyed, is only transferred between different formats. And we're also going to talk about the potential energy become a kinetic energy from the microbiology standpoints. Let's say proton motive force, which is a typical, is a potential energy become a kinetic energy. That's the first one. Okay, second law. Second law, we just say the very simple. Disorder, increase. That's the second law. And bacteria same as a human being. In the lifetime, the disorder is always increased, and they can come back it and put it back. If there's one day they cannot to put the disorder go back, then they will be dying. So it's very simple. This comes out with a very easy and very important but a little bit hard understanding format, which is delta G equals delta H minus T delta S. Okay. It's not a physics class, but I would be using my way to explain to you. Okay, what is delta G? This is free energy required to do cellular work. Just be very simple. That's free energy. Okay, what is delta H? This is called enthalpy. Okay, what is that? This is heat amount, or we say heat content at a fixed volume and pressure. Obviously, there is a fixed temperature. That's called enthalpy. Okay, what is this T means? This is something tricky, because in our real life, we talk about degrees Celsius, we talk about degree Fahrenheit. This is not. This is international temperature standard. So what is that? That's Kelvin. The Kelvin equals degree Celsius at 273. That's a T. What is delta S? That's called entropy. Okay, that's entropy. That means the amount of the energy cannot work. Okay, now you learned the conclusion. If delta G less than 0, okay, which means it's negative, okay, that means spontaneous reaction or biochemical reaction is happening. If the delta G more than 0, that means positive value, then spontaneous reaction will not happen. And then if delta G equals 0, we reach equilibrium status. Okay, this is the conclusion. But it is hard to understand. Why it is hard to understand? The reason is, this is back in 1920s or even earlier in the 1800s, is people using thermodynamic physics to explain the biochemistry reaction and even biology. So it is an interdiscipline between two subjects. So that's why it is difficult to understand. And you learn this in biology 101, biochemistry, organic chemistry, different classes. You know the conclusion. But how we understand about that, so I want to try to help you to understand about that. And you can look at all these slides. It just tell you, oh, it's positive, negative, what it is. So what this means, we certainly could draw something to tell you. Okay, let's talk about this delta H first. When we talk about delta H, we are assuming T and the delta S stay the same. So what happened? Let's talk about delta H. If delta H decreased, T and the delta S stay the same, it will bring delta G become negative. This is understandable, is that right? So let's say this whole number is 100, let's just say. Delta H is from 100 to 90. Then delta G becomes negative. Now how we explain it? This is very simple. If I have a ball right here, the ball goes down. Is that spontaneous happened? Yes. And this ball, the delta H, is decreased. So that's easy to understand. The ball coming down spontaneously happened. This delta G less than 0. That's the first one. Okay, how are you going to explain T? When we talk about the T, we assume delta H and delta S are the same. So obviously delta T has to, obviously the T has to increase. What's the example? I have a cherry bomb. July 4th, have a cherry bomb. Then I'm lightning it. What happens? Oh, boom, like that. Spontaneous reaction, delta G less than 0. Because this T increased. When I lightning it, I get the heat. The temperature increase, then bomb. So cherry bomb. Oh, July 4th could explain the T. Okay, what is this guy? What is delta S? And we talk about delta S is entropy, which means the amount of the energy cannot use to work. In other words, this order is increased. So how do you understand about that? When we talk about delta S, we're assuming delta H and T stay the same. Simply, this has to be increased. Okay, what is that one? You can easily understand. Is I have a box. I have a block there, and I have all these balls. Okay? And what happened? So one day I lift the block. This is organized. And this is going to be disorganized. When this one is lifted, the ball goes everywhere. The ball goes everywhere. That's how you explain the delta S. Okay, so that's an easy way, it's really easy way to understanding this equation, what this means. Now, in the biology area or biochemistry area, it comes out some of a very standard equation. Let's say I have an equation is A and B generate C and D. And you learn in your chemistry class, it's coming from the constant, equilibrium constant equals the concentration of C multiplied by concentration of D divided by concentration of A and with concentration of B. And regarding the delta G, they come out with a very standard formula, which is minus 2.303 RT and log 10K equilibrium. And what is R? This is a heat constant, 1.98 kcal per mole, and that is the temperature, Kelvin, and this K EQ is equilibrium constant is right here. So, because it's a negative at the top, what happened? If this KEQ is more than 1, then this whole formula will become negative. Okay? That means delta G will be negative. Spontaneous reaction will happen. This is called exogonic reaction. Exogonic reaction will happen is ATP becomes ADP. If KEQ between 0 to 1, which means less than 1, this whole thing will become negative. And because negative at the beginning, so negative and negative become positive, which means delta G is more than 0, then endogonic reaction will happen. And when this happens, is ADP synthesized becomes ATP. Okay, so I want to explain this to you a little bit, okay? So it's negative here. So let's assume it. KEQ equals 10. So log 10 equals 1. Is that right? The whole thing is negative. Second scenario, if KEQ equals 0.1, then log 10, 0.1 equals what? Minus 1. Is that right? Because that equals this. Okay, this whole thing equals this. So, minus become positive. Negative become positive. And this is more than 0. Okay, this is a very standard thing explained this happens in the biochemistry reaction. So just give you some of the conclusion. They at the beginning, they come here and then they go here. This, in other words, you know, this is called Gibbs free energy principle, or rules or equations, whatever they call it. This is more general for thermodynamic, and this is more focused on biochemical reaction or chemistry reaction. Okay, so that's something like an opening remarks. And we have a slide to talk about here. So a couple of slides talk free energy reaction. This we already talked. Every single items, what that means, chemical equilibrium, and this is what I just drawed. And then this one is endogonic, exogonic, the negative, positive. You can figure it out by yourself. It's basically the mass. Okay. Now we want to talk about is energy currency. Okay, so this we're going to have to go. So the next topic will be, folks, talk about the energy currency. So what that means, what it generates, how they come from. So this is a very interesting topic. We basically is review what you learned using a different standpoint. So energy currency. Everybody knows is ATP. So first the question is very simple. What is ATP? That's a very easy question. The people in the high school, they should know, but lots of people doesn't know because we always talk about ATP. This is 5' adenosine tripolyphosphate. Which tripolyphosphate. Now what's the structure? That's what I always like to draw because it's important. Okay. What is this guy? Go here, go on the top, NH2, N, then we have N, we go here, we have N. Okay, then what do? You go, then you go here, and you go here. Okay, then you go here. And we can label them even. So we can label them 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, then we go. Go here. You're going to have this guy comes out. Okay, go here. Connect it. Okay, we go here. We have an H, OH, H, OH, go here H, CH2, and go here O, then what you do, P, double bonds, go here, O, then P, double bonds, go here, O, then P, double bonds, go here, and O. And lots of the textbook, this is going to be like this, like that. Okay, what is this guy? This is in your biochemistry class. They always say you're going to draw DNA or RNA. It's just a little bit complicated than that. What is this? This is the adenine. This is A. What is this guy? That's a ribose. Okay, what is here? Tripolyphosphate. So it's very easy. It isn't difficult at all. And the whole thing, that's ATP. If you start from here, that's ADP. Only this side is AMP. So that's the structure. And the structure is right here. And we can draw the same thing. It's not difficult. Now, by the way, I want to mention, this is A. We have C, we have T, we have G, we have U. They could potentially all as an energy currency. It looks like this is a dollar, this is a pound, this is euro, yuan, this is Canada, dollar. It's all could be used as an energy currency, but most of the time we're using ATP as a more often energy currency. Okay, so that's the first thing you need to know. Adenosine 5' tripolyphosphates. Now why 5'? Because 1, 2, 3, 4, and 5 are disconnected to here. Okay, so that's 5' adenine tripolyphosphate. Okay, so we talk about here already. Now we want to go here, talk about this guy. The role of ATP in the metabolism, and we also want to talk about this potential phosphorus transference. It is very interesting. So what happened is, this is what happened is ATP can hydrolyze, become ADP and phosphates. And what is the potential energy of this? If you want to have this happen, this is negative 30.1 kJ per mole. If I'm going to do is an absolutely value, which means this becomes 31.1, then we give them another terminology. We call this the phosphor transfer potential force or value, we can say about that. Okay? So then we did a lot of research. What they find, there are some chemicals, for example, 1,3,5-phosphor. Okay, this is 30.1, okay? 1,3,5-phosphor glycerate. They find that this delta G, and this is the phosphor potential. This is very high. This is kind of like minus 61, 71, 79.3. This is become 79.3. Then there's another chemical, phosphor pyruvate. And they find the delta G is minus 71.1, and this is 71.1. And they compare to 31.1, the phosphate potential transferring power is larger than that. So what this means, it could go this way as a reaction. So instead of ATP hydrolyzed become ADP and the phosphates, it will happen is ADP with phosphates becomes ATP. And this phenomenon we call substrate level phosphorylation. Just use P instead of phosphorylation. Okay, what is this guy? What is that guy? Do you know where that comes from? So, we have glucose. We're going to talk on Thursday, okay? Glucose. We go here. Is that right? It's pyruvate. What's the name of this one? Glycolysis. Okay. Somehow in here is 1,3-biphosphoglycerol. Somehow at the bottom is phosphopyruvate. So what is that? What is this guy looks like? What is this? 1,3-biphosphoglycerol. What is sorry, this is going to be phosphoenolpyruvate. Sorry, I forgot. What is phosphoenolpyruvate? That's phosphoenolpyruvate. Then what is pyruvate? Is that right? So that's where it comes from. These two chemicals are very important. They could happen, simply have ADP with phosphates generate ATP in a simply chemical level to do a transfer. Because their phosphate transfer potential power is more than ATP become ADP and phosphate. So the reaction could go the other way. Now, there is some other chemicals. They looks like names phosphate. For example, glucose 6-phosphate. Okay, fructose 6-phosphate. These chemicals, they have a phosphate. Looks like it's a higher level phosphor transferring chemical, but they cannot do this work. They can't do this work. The reason is the phosphor transferring power is lower. This looks like 13.1, this looks like 6.1, and this is both less than 30.1. That's why you cannot do it. And this is well explained right here and well explained in this table. And this comes out a good definition and the good explanation what is substrate level phosphorylation. And I know you guys learned in the biochemistry class. Everybody told you what is substrate level phosphorylation. Is ADP becomes ATP without electron transport chain. And I used to have a joke. I cannot say this joke anymore. This is like I ask you why he's a boy, you tell me because he's not a girl. Okay, it's the same thing. You learned all your different classes all kinds of the time. People tell you about that, but what is really substrate level phosphorylation is this. You have to compare phosphor transfer potential power. You cannot say, oh, this is not apple because this is apple because this is not orange. Okay, it's just the opposite way, not really. There's a story behind that. And there's lots of the work done by 1920s using physics thermodynamic theory to get a conclusion. And this thing comes out here will be the table. So you can see left side is listed all the phosphorus molecular, and you have a delta G, which is a hydrolytic removing of phosphate and the phosphate transfer potential. The phosphate transfer potential is just an absolute value of the delta G, which means you took out of the minus, become a positive. Okay, so this is a very important slides, but this whole thing tells you is substrate level phosphorylation. Okay, now let's talk about this guy, oxidation reduction potential. This is another thing. Basic chemistry knowledge, but lots of people don't understand or still confusing. So we are using the simple example could be explained to you what this happens. So we're going to move here. We need a large space. Okay, so oxidation reduction. Let's just talk about this guy. We talk about the OR reaction. Oxidation reduction reaction is always coupled. 99.9% of the biochemical reaction, this is all oxidative reduction reaction. A very simple formula is A and B become, and also it's reversible most of the time, C and D. And I just gave you a very simple example. If A becomes C, lost electron. Okay. Can you tell me what is this one for? And I always say this. Let's just make it easy. Let's say gain electron. Okay. Just say gain electron. I gave you a very simple example. I don't know whether you know what is a GRE test. Graduate record exam. If you go to graduate school, Before COVID-19, that's a required test. So I came from China to United States to Colorado State University for PhD study. We're required to take the GRE test. This is gives is gain electron means reduction. Obviously, loss electron is oxidation. So what means gain electron? What means reduction? So look at all you guys' face. It's very young. That's a reduced status. If it's 80-year-old grandma's face, looks very dry, not much energy, is lost electron. So that's a very simple example. You see the apple, fresh apple, is reduction, reduced status, lots of energy. When you see an apple has been spoiled,